And that's if you want to start quantum computation, this is the book that I recommend, Nathan Nielsen Chong, which is the Bible of quantum computation. And it's David McMahon, the Wiley publication, and quantum computing explained. He talks about quantum computation in a very intuitive manner with lots of examples, exercises, and also problems. And the first chapter is brief introduction to information theory. For me, it's just like the problems is way too easy, but it's a good start, way too good start, and almost comprehensive. So, a brief introduction to information theory. What is an information? The most basic form of information is bit. Yes, no. 1, 0. And we want to quantify information. And we need a concept known as entropy, which is a measure of disorder. And information is the opposite of disorder. For example, if you have a message M, which has M different states, and how many bits of information you can quantify it? It's at least 2n you need. For example, 1 is not, if the M is equal to 1, it's not an information, it's just like obvious thing. If M is 2, that becomes a difference, like it has 2 states. For example, 1 and 0. So I'm gonna use 2 to the n equal to 1, which is 2 to the 2, 2 to the 1, bigger than equal to 2. And so I need 1 bit, which is like, x. X can be 1 or 0, and n here is equal to 1. Then for 4 bits, for 2 bits, you have 4 different states. 4 is equal to n is equal to 2. There are some like a question, what is entropy exactly? What's the unit of entropy? We need to go to thermodynamics. It's necessary to do that because it's going to make it teaching comprehensive. And how exactly entropy is related to information. But for the 0, 0, 0, 1, 1, 0, 1, 1, it's 4 different states with 2 bits. And if I want to quantify m 2 to the n, if I want to take out the n, what I can do, I can take the logarithm from base 2 from the both sides. If I take logarithm base 2 from m, is log of m to the base 2. And if I take the logarithm base 2 from 2 to the n, this becomes n log of 2, 2, which is n. So n, which is the number of the bits, is equal to logarithm of the states that you have to the basis of 2. This is the first attempt to quantify the information in the message. And entropy and Shannon's information theory. we introduce something else, which is called likelihood. We say that a message that is unlikely to occur has a low probability and therefore has a large information content. And a message that is very likely to occur has a high probability and therefore has a small information content. The information content of a message is I, and to the 2, probability of its occurrence is P, and the information content of the message M is I, and the probability of its occurrence there you go. The question is, like, probability doesn't have, probability is like, number of the things that happens over S, which is all the set. This is like 2 units go away, so it doesn't have, it's just a ratio. It doesn't have ratio between 0 and 1. It doesn't have a unit. So the logarithm of P probability based on 2 doesn't have unit either. But this is like information content of a message. It's a relative measure. It doesn't have a unit. And I didn't go to the Shannon entropy because I've not studied it well, because Shannon entropy uses the random variables. That's not a problem. That's like easy to explain. But I don't understand still where does the equation come from? I just go through it briefly, and to the Shannon entropy, this beautiful thing. First of all, why do we define the Shannon entropy? Let's say you have a random variable. What is a random variable? It's a function. What is the input of the function? Like, let's say you have probability outcomes x1, x2, x3 to xn, and each one of them has a probability assigned to them. It's like P1, x1 happens with P1, x2 with P2, P3, and Pn. And the normalization of the probability, the add of the probabilities, the sum of the probabilities from 1 to n needs to be 1. But the outcomes, like, it can be anything, doesn't matter. And the random variable, let's say x, means that the probability function that x, this random variable, is equal to x1 or xi is pi. So it means that what's the probability that this is just a random variable, it's a variable that assigns to let me correct myself, it assigns to the outcomes. And when I say like the probability, what is the probability of x1 happening, outcome x1 happening, it means the random variable x is going to be equal to xi, and the probability of this based on the probability function is going to be pi. So it's kind of an abstract notion. I'm gonna give you an example for that. It's like we toss a coin, it's whether going to be head or tail. Why did we define the random variable? It's just a measure, it's a means of like facilitating the process. The head and tail is x1 and x2, the outcomes. And the probability of head is, let's say it's not a fair coin, it's like a crooked coin, whatever, it's like 40%, and this is 60%. P1, P2. So I say that P of x equal to h, it means the outcome is going to be head, it's P1, which is 40%. And P of x equal to tail is going to be P2, 60%. There you go. That's it. So, what it has to do with the Shannon entropy. The Shannon entropy and it's probability function and probability distribution. It's totally fine, yeah. And it's this h of x, the random variable in here, is going to be equal to minus I pi log of pi. Shannon entropy function as a measure of the amount of uncertainty or randomness in the signal. For example, if we have x1, x2, head, tail, each one of them has 50% probability, then 1/2, it's going to be the Shannon entropy of this random variable is going to be equal to minus 1/2 log of 1/2 minus 1/2 log of 1/2, which is going to be minus log 1/2, which is going to be the minus log 2 to the minus 1 is going to log of 2, it's going to be 1. But this is not a very good, yeah, it's going to be 1. But if there are 3 equal possibilities, it's going to add, like it's going to go up. It's going to be 1.585. If it's all the same, it's going to be 0. So we need to explain that, like, we need to have a deep understanding, and then we're going to get to the average bit rate, conditional entropy, mutual information, and the probability basics is very easy, so I'm not going to get into that. But the next time, what I'm going to do is to answer these questions. Where does the Shannon entropy come from, the equation? At least what's the intuition behind it? First, second, 12 minutes past. And second, what's the relation between entropy as a notion of thermodynamics, and we don't need to pass all the advanced thermodynamics. All we need to know, what is the equation for entropy and how it is exactly related to the basic information of bits and Shannon entropy, how these things are related to each other. That's it. And we say that based on the, what was the name of it? I forgot. Wait. The information contents, I minus log of p to the 2. It means that if the probability is way too high, then let's say it's almost, I don't know, it's 1/2. This is going to be 1. If the probability is 0, I is going to be really high. So if probability is 1, it's going to be 0. So it means that the probability has a inverse relationship, reverse relationship with amount of information. The higher the probability to the 1, the information is lower, and I is going to be between 0 and infinity. And if the probability is almost 0, it's almost 0. Then the information content goes very high. But this is this is a questionable measure. I don't want to measure question everything, but it doesn't make sense to me. I cannot just memorize it. What's the point of memorizing this without understanding it? Because what I'm trying to say basically here is, we say that if every single day it rains, and the probability of tomorrow raining is very, very high. So the information content of that is low. But let's say let's change the events. Like, you know, my girlfriend dumps me every day, and since 1 year ago, like it's a toxic relationship hypothesis. But each time the information content that I have is so shocking, and so I don't become numb, and it's so shocking and it's so important. So I don't understand what's the measure here that we say if the probability of something is very high, the information content of that is low. For example, the probability of having like a thunder in Orleans in the United States or Florida is very high, but information content of that is high too. So they are not necessarily always in direct relation with each other. Like, you know, maybe the probability of something is very high, but the information content of that is high too. So maybe I'm like, you know, making a logical fault here, not logical fallacy, but logical fault. Like, I'm making a mistake here. But I don't understand why, like, if the probability of something is very high, the information contents of that is very low. There are some exceptions, might be sometime. That's it. Bye.